Paper folding can be used to do things in math, things that you can do if you have a compass and a straight edge, and some things that you can do even without, that you couldn't do with a compass and a straight edge. And there were a bunch of axioms that that tell you what sort of legal sort of folds you can do with paper folding. And one of them is that if you have 2 points, it's permitted and possible to make a fold that goes through those 2 points. It's kind of like making a line through those 2 points. The second axiom is if you have 2 points, you're permitted to fold the paper so when you make the folds that folds this point on top of that point, and you have to kind of look through the paper to do that, it creates this line. And geometrically speaking, that line is the perpendicular bisector of the line segment that would connect those 2 points. The third axiom says that if you have 2 line segments, and it helps if they're the same length. So here I have 2 sort of congruent line segments, but if they're not congruent, this works also. It's possible to make a fold that will put this line segment right on top of that line segment. So this point would end up on top of this one, and this one would end up on top of this one, and the entire line segment's on top of that one. The fold looks something like that, and geometrically speaking, that fold is actually the angle bisector of the angle that would be created if you continued those lines. Now, if the lines are not the same length, it's still possible to fold this line so that sort of this portion ends up kind of like over there, and that fold would be the angle bisector of the angle formed by the continuation of those lines. The fourth axiom says that if you have a line and a point somewhere not on the line, it's possible to make a fold. See, you can always make a fold. You can always make a fold perpendicular to the line by folding the line kind of onto itself. But one of those folds would also go through this external point. So you can kind of like fold this line on top of itself in such a way that it passes through that point also. So that's the fourth axiom. The fifth axiom says that if you have 2 points, let's say P and Q, and some line, I'll call L, sometimes, but not always, it's possible to fold point P onto the line in such a way that the fold goes through point Q. So, for example, if I fold P to this spot, the fold will go right through Q. That's actually not the only way to do it in this case. If I fold P to this spot, the perpendicular bisector, or the fold, which is the perpendicular bisector, will go through Q. So there's more than one way to do that. That's what axiom 5 says, that if possible, you're permitted to do. It's actually not easy to do sometimes. Sometimes it's impossible. Now, when you do the folds, it should be noted that you here we create the fold that accomplished it. It put point P onto the line, but we don't know exactly where it went after we make it. Like we do a fold, P goes onto this spot here, and we make our fold, and we see P sort of on the line as we're sort of looking through it. But we don't actually know where the point is necessarily. So sometimes we can do, if you want to actually get that point without like sticking your pencil through the paper, you could make a second fold where you would use axiom 4 to fold. Let's make this fold a line now, and now I fold that line onto itself so it goes through P, and that would actually get me the point that P got folded onto to create the fold that went through point Q. So just keep that in mind. I want to say a little more about axiom 5. Here's the 2 points. Here's the line. And a trick for locating where to fold P would be to imagine, or to imagine a circle. Whoops, to imagine a circle that's centered at Q that goes through point P. If you fold P to this spot, then the perpendicular bisector will go right through Q. If instead I fold P to this spot, then again the fold goes right through Q. Now the reason that works is somewhat complicated. If I fold a point anywhere onto a line, there's going to be the fold's like a perpendicular bisector, and any point on the perpendicular bisector is going to be the same distance from the point that I had to the point on the line that I folded it towards. For any point, that will be true. So back to this other side, if the fold also goes through Q, then if the fold also goes through Q, here's an example. Every point on this fold is the same distance from here as it is from here, and that includes point Q. But Q to P has a certain distance because Q and P were just given to us, so whatever that is, if that's like 3 inches or something, then Q to this other point will also be 3 inches. And then certainly these 2 points will be on the circle with Q as the center. Same thing is true if I choose this is my point to fold P onto. Any point on this blue line is equidistant from P and this sort of P prime here. But Q is on. If Q's got to be on the fold, then those have to be the same distance. So again, if this was 3, this is going to be 3. So all 3 of these points, P and the 2 sort of special points, end up on this circle. So in a sense, axiom 5, if you do it, what you've ended up accomplishing when you find a fold from P to the line that goes through Q. This one's not good enough. When you find a fold that actually goes through, that will also help you find, if you make a now that we have the fold, if I fold make a perpendicular bisector here, and we get this point, that is one of the points, one of the intersection points of the circle with Q as the center that goes through P with this line. And the other one, which is over here, if that's my fold, and I make the perpendicular sort of through that fold to get the actual P point. Those 2 points, the 2 points that you can fold P to so that the fold goes through Q, those are the 2 points that would intersect the circle. So if I have a situation where I have to find, using paper folding, a place where a line would intersect with some circle, axiom 5 is a way of doing that.